We have Maria Mingallon. Maria is a senior designer, senior engineer with Arup in Montreal, but also has a kind of design background. So Maria studied in Spain, her undergraduate degree in engineering, and then did a master's degree at the AA in London with a focus on advanced computational design. Would that be correct? And is now leading the engineering group at Arup in Montreal.
The structural group.
The structural group, sorry, what did I say, the design group. So the structural group at Arup in Montreal. For those of you who don't know, Arup is, I would say, one of the kind of biggest and most prestigious design engineering firms in the world. For those of you who are not familiar with Arup, it's a firm that you should be familiar with because of the kind of work that they do. It's incredibly interesting work, very sophisticated, both from a design perspective and a tools and technology perspective, I would say. So I think we're very fortunate to have Maria here today to speak to us about her work. She's also been adjunct faculty member at McGill University in Canada, and I think she's going to talk about some of that work, some of the big projects that she's worked on, the 2012 London Olympics. I think it's amazing to be able to have someone here to talk to us about the kind of work that happens at McGill in a sort of student perspective and at that scale, all the way to the kind of largest projects of these infrastructural projects in the world for the Olympics. So we're very fortunate. I'm going to leave it there and let you take it. Remember, this is all about conversation. So hopefully you guys will generate some questions and we can have a little bit of conversation and a debate at the end of this talk. That's really kind of the main point of having these lunchtime lectures. So please do engage in some conversation at the end. All right, Maria, please. And if anybody wants to come forward, there are a lot of seats forward.
Yeah, I don't bite or anything like that. Well, thanks a lot, Tristan, for that introduction. I know that everyone says this when they come to say lectures, that but it's a great pleasure to be here with you, with all of you today. So thanks very much for inviting me here. I'm hoping that I'm gonna be able to, perhaps enlighten you or inspire you today, at least for what's left of the Friday, maybe for the whole weekend, who knows? And maybe it's not such a difficult thing because Fridays are always inspiring in a certain way, right? So let me start by asking you two questions. How many of you think that an artist can be an engineer? And how many of you think that the opposite is also true, that an engineer can also be an artist? And you don't have to necessarily, say anything or respond to it. But the reason why I started with this is because I think there are a lot of people that tend to think that arts and engineers are completely separate, and they tend to put them, artists and engineers, into two different boxes. And they tend to define art as perhaps something just to do with aesthetics and beauty and form. And engineering just has something to do with efficiency and economics. And I'm saying just, okay? Because I don't think it's just about that in either discipline. And I think that actually artists, architects, and engineers and the whole design community should be very related to each other and should really work in a collaborative manner. So, the reason why I think they are indeed related, it's because engineers, in order to do their work, they really need to be continuously thinking about new ways, new solutions to existing problems and new solutions to changing problems. And an artist is also always chasing new ways of communicating thoughts, feelings, and ideas. And so in reality, they are both pioneers. Right? They're all the time chasing, or they should, if they are good, accomplished artists and accomplished engineers, they should always be looking for new ways of doing their work. And in fact, when you look back in history, hundreds of years ago, artists and engineers were not separate, were sometimes the same person. I mean, I'm sure you all know the example of Da Vinci. Who doesn't know about him, right? He wasn't just an artist or just an architect or just an engineer. In fact, he was a true inventor, a true maker that was able to combine all of those disciplines into one person to do his work. And I wonder what happened from him to more recent history. And I believe what happened is that advancements in technology have actually, sadly, relegated engineers to a corner, and sometimes relegated them just to do calculations, and I would say actually execute calculations. And I find that quite sad, because I do believe that the actual integration of all of these disciplines for engineers, architects, and overall designers is the best way of actually achieving good design. And good design is good for everybody, right? For clients, for ourselves, we feel more accomplished, as well for public who is going to use it, etc. Now, in the last decades, we can see that there has been a shift towards integrated design, which a lot of people think that it's something new, but in fact it's not new, and that's what Da Vinci was doing, and that's what Sir of Arup was also doing at his time. But integrated design is coming hand by hand with advanced computation and with digital fabrication, and it's really setting a common ground for architects, artists, and all types of designers to collaborate in the same, in a very collaborative manner. So I think, you might be wondering, so how is advanced computation really helping into integrated design? I'm not gonna say, or I'm not gonna argue that advanced computation is just what you need to achieve integrated design, but it certainly helps. So it's not just that is going to guarantee that you're going to have an integrated design approach, but it's certainly going to help artists, architects, and engineers be on the same common ground. And again, you might be wondering, how is that possible? And I'll tell you a little bit of my story. When I went to engineering school, I learned all of these different programming languages, such as Java, HTML, Visual Basic, Fortran. And it was only when I went to the AA, about 4 years later, that I was actually realizing that architects were also using those, and that I could speak in that language. Before that, I was practicing, I was working at Arup, and I actually never came across a situation where I could collaborate with an architect talking that same language, the language of coding. So I think there is clearly a shift towards architects, artists, and engineers using coding as the language that we all kind of speak and can collaborate with. And at the same time, because at the end of the day we are makers, right? Like, I think architects ultimately build things. The profession is there to build things, and so are engineers. If we actually miss the opportunity to link coding with digital fabrication, then coding becomes actually useless. So unless you really understand digital fabrication tools and what they can do for you today and what they are going to be able to do for you in the future, you're not going to be able to make the most out of the coding that you're learning. So I guess enough of all of this philosophical talking, and let's see if I can actually show you a few projects where you can't really distinguish art, architecture, and engineering, because they are, or I think they are, fully integrated. And I'm going to start with this, which is a research project that I did at the AA during my thesis. What we did is, as part of a biomimicry study, we studied the architecture of the Dragonfly wing. And you might be thinking, well, what is it in there that is actually going to teach you something about how you build something else? And what we found is that it was actually a fairly interesting structure, and you can see here that it is highly complex, but it is also fairly simple in the way the geometry is executed for making the Dragonfly a very efficient animal in passive flight. When I say passive flight, what happens is that the Dragonfly, when it flies, it doesn't tell the wind to actually do anything more complex than just this flapping. But the wing is designed in such a way that it will camber where it needs to camber, and it will be rigid where it needs to be rigid, so that you actually get to move within the fluid of air. And you'll see that in a video that I'm going to show next. But before that, as I said, there are some areas in here that, because they are tessellated with hexagons and pentagons, they are there to make it more flexible and also to fill space in a more effective way, because we all know that the most effective way of filling up space is hexagons, right? And instead of having hexagons on all of this front part, because this has to resist fairly large wind loads, all of the cells in here are square cells or rectangular cells, and they are perpendicular to these main vanes, which are in fact taking all of the, or pretty much all of the wind load. Now, you might think that the wing is actually flat, because to human eyes, it looks flat, but it's indeed not the case. The wing is actually corrugated, and you can see that through all of these sections taken at these locations in the wing. When you look at the microscope, you actually see that all of these corrugations are actually quite intricate, and you have different joints, components as well throughout the wing that allow for certain movements and do not allow for others. All of that articulation is really making the wing an object that can make the Dragonfly move and maneuver the way the Dragonfly wants, out of a fairly simple movement throughout its flight. So how does it really work? I'm showing you this diagram so that you can understand better the video that comes next. What happens is that if you imagine if you're in a swimming pool and you try to swim and you try to advance, if you just do this, you're not going to get very far, right? What you need to do, and you know this if you've ever swum, which I assume you have, is that you actually have to create thrust. And to create thrust, you have to do a sort of movement that it's going to impulse you, right? You need to have, you need to basically create a wave on the fluid. That's what the Dragonfly is doing in the fluid of air. And so what you see in this simulation that we did using our in-house structural software is the harmonic vibration mode of the wing, okay? So what we've done is we put the wind load and we put its own weight, and then this is how the wing actually moves. And you can see that there are areas that are flexible, fairly flexible, to create that thrust, right? To camber and create that thrust, while this edge here is remaining quite rigid. And you can see that it's creating quite a nice stiffness in that area to be able to resist all of the wind load that comes this way and also this way.
The bottom is the leading edge, correct?
Exactly, yeah. This is the leading edge, yeah. Now, how we actually come to use all of this thinking into architecture? Well, we used a very limited amount of all of the things we learned throughout the study of the wing. And what we used for this inflatable structure, which actually was part of a temporary pavilion for the theater at Jena for one of the events during the summer, the opening events for the theater festival in Jena in collaboration with the Bauhaus, is that we use the idea of having the square cells on the periphery of the structure, while the pentagon and hexagonal cells were actually creating flexibility. So where the structure needed to actually camber and be flexible, we use hexagonal cells. And where it had to be more rigid, we use the square cells. This is the pavilion as it was installed on the facade of the existing theater in Jena in Germany. And this was a project that was actually done in collaboration with artists, architects, and engineers. So, you know, the people that appear in the first photo that were acting were actually not professional actors. Some of them were photographers, some others were writers, some others were artists, and some others were architects and engineers. The next project that I'd like to show you is a sculpture that we did helping artist John Gray out of Seattle. The artist came to us with the idea of making a sculpture out of a historical boat that has actually been fairly famous for the history of the United States and especially of Seattle, and that was the Wawona ship. What happened is that they wanted to keep it, but they couldn't keep it in its original shape because most of the wood that was actually on top of above the sea level was in fairly bad condition. So what they did was basically dismantle the ship and keep all of the planks, and then they said, well, let's make something, let's make a sculpture out of it. So these are some of the first models that the artist put together. His idea was to create a sort of tube towards the roof that could actually filter light through, like an oculus or an opening, and that had to be actually looked at very carefully because Seattle is also a seismic zone, as you might know. It's pretty close to the San Andreas fault, and it had to be designed for seismic. So this joint that you see here is actually to make sure that the sculpture can actually swing this way or this way, pretty much in any way, on this plane, while it's being suspended from the roof, so that it doesn't impose on the roof as a new column, and therefore it tries to get loads and tries to change the way the existing building, the existing museum is built. Now, one of the key things that you might actually be wondering is how do you actually get from straight planks into a doubly curved surface like this? Right? So what we were asked was to do this out of this. How do you do that? Well, by carving, of course, but that's not what I mean. We had to come up with a system, basically, of how we were going to lay out all of these planks in such a way that we could create a surface that was gonna have to change curvature both in this axis and this axis. Right? So we did that by basically segmenting the sculpture into different sections, and then we had to limit the actual carving, or consider the limitations of the CNC machine as to how much thickness it could actually carve for each of the planks, and that happened in this axis, and that happened again in this axis. So the idea was, as I said, we had the planks running this way, we were gonna carve them this way and also this way, and then in between each of the segments we would have steel sections that were actually going to support each of those planks and bring all of the forces to the roof. So basically all of this sculpture is suspended from the roof and is suspended through these ties, and then these ribs are therefore horizontal restraint, and also to basically pick up the forces. These are some of the pictures of the CNC at work. So as I was saying, we had to consider where were the limitations in the thickness of the material and basically how much we could actually carve out before we run out of the total thickness of the planks.
Are those double sandwiched beam planks right there that you're carving through, or just single planks?
These are single planks, yeah.
And then, so the planks are going to be, they're going to be
Then there was another layer of, let's say, craftsmanship that the artist had to do, and that was adding in all of these holes through the planks so that you could actually filter the light through from the roof onto the rest of the room. So he added all of these holes and cones and then started to actually carve them manually. That was done by hand, and that was the artist's choice, because that way he could actually, I guess, add in a bit more of his own personal touch, as opposed to just doing it with the CNC. But you know, it could have been done with the CNC as well. So these are some of the panels when they are finished or about to be finished. And they do look fairly nice, like they're bringing out all of the nice brightness and glossiness of the original wood material.
But the orifice is adhered, correct? That's a separate part that has been adhered to the link?
Yes, yeah, of course. So all of this, it's a separate part, yeah. Like it's basically being glued onto the wood and then it's being carved. Yeah. So I guess if you were to look fairly close, you could see that there would be a seam in here, but
and the grain changes. You can see where the grain is changing.
Yeah. These are some of the pictures of the installation of the structure. So those are the steel ribs that you saw in that diagram in Rhino. This was all done in Rhino and Grasshopper, which I'm sure you're familiar with. And that's how light started to filter through the sculpture. And these are just some pictures of the finished product. And as you can see here, that's the joint condition that I was talking about at the very beginning, where sculpture is being suspended from the roof. But then this here, with the little space that we're leaving in between the opening and the rod, is actually what we can call a seismic bearing. Although it's not really bearing, but you see what I mean. Basically, this can move on this plane in any direction, okay? Okay, so next project is actually quite an unconventional one because, first of all, it's made of paper. So this was something we did out of the Montreal and Toronto office, and when I had to talk to the buildings director about this little competition and little call for entry, building with paper, and about suspending a canopy of 5 meters over an 8 meters opening in a hall in Toronto. If you talk to someone like that and you mention, yeah, we're gonna do it in steel, or we're gonna do it in wood, or then it's okay, you know, it's not a problem. But no, this time we are actually thinking of doing it in paper. All right, okay, that doesn't seem very safe. So what are we doing here? This was an initiative by a group of artists and architects called Pulp. They basically organize several, you can say, parties or basically little competitions for all Toronto-based artists to participate in. And the only requirement is that you have to build things with paper or cardboard, and it has to be something that has been used before. So you're essentially upcycling cardboard or paper. And in this case, what we decided was to use A1 sheets that were used in the office and create an origami structure that could actually span the 8 meters that we needed to span. So I'm gonna actually play a little video that will show you. This was a video that we did for the entry.
Hi, my name is Andrew Chung, and I'm from Diamond Smith Architects.
Hi,
My name is Mingallon, and I'm a Senior Structural Engineer at Arup.
Hi, my name is Mingallon, and I work for Arup.
And we're here to show you our entry for the pulp art party in 2014. What is the pulp art party? It's an event in 2014 that combines cutting-edge local design and live music, raising money for a good cause. It exclusively uses reclaimed materials, combines art and design together. Our team uses the power of the internet, and we're located in both Toronto and Montreal. This year it's going to be held here at the Great Hall in Toronto. Day to day, in creative professional offices all around the world,
Ideas are born.
Sketched and communicated through the medium of paper as experiments, as fully fleshed out drawings communicate the intents of designers, architects, and engineers.
And move it to fully formed, built reality.
however, throughout the design process, not every approach is taken, and in the course of finding solutions, a multitude of possibilities, drafted, drawn, or sketched onto the medium of paper are discarded, redistributed to forgotten areas, and disappear.
Every drawn idea, whether discarded or found to be a mistake, represents an attempt as designers to push solutions for the benefit of the public and our environment.
They form, in essence, a wish list of desires for better living for the future.
What happens if we could harness these images and use this incredibly vast volume of paper towards another creative endeavor?
By redirecting the approach of these thoughts and sketches, we believe that we could give life to these desires and broadcast them in a positive manner.
Request for proposals is joint Diamond Smith Architects and Arup installation, where as designers, architects, and engineers, we use the amount of paper discarded each day as a means to enact positive design for our environment.
If we are to truly think positively for our environment, we must engage in the idea of sustainability in its most basic form.
Our intention for this installation is to reuse and recycle A1 sheets that are used, printed, and discarded every day towards markups, presentation drawings, and submissions, and refold them into an origami-like structure that conveys every design idea into a form.
In this way, the installation becomes a public display of every attempt to solve problems for the public at large. We strive to improve our environment for everyone.
We're really excited to try out new toys and explore new ways to rethink the use of materials. We're looking to push computational design, digital fabrication, and elements of paper. Who knows? Maybe this could be a prototype for something in the future. With this opportunity at the pulp art party, we think these thoughts and ideas can be displayed proudly, contribute towards local designers and artists, and promote sustainability within not only Toronto's design community, but Toronto itself at large.
Good design accelerates the acceptance of good ideas.
We think being sustainable is a great idea. Do you agree with us? RP is your opportunity to make this change happen.
From now until the end of April, at both of our offices, we're going to be collecting A1 sheets in these bins here. Thanks very much for listening. Merci beaucoup.
Okay, so basically, as you heard, what we did is collect all of the A1 sheets that we had in the offices, in the Arup office and the Diamond Smith Architects office as well, throughout several months. We basically formed sheets of 5 A1 each, and we started to fold them. And saying that, it's kind of simple, and it sounds all very straightforward, but it wasn't like that, of course. We found that a lot of the modeling that we had done through Grasshopper and various softwares it was good to inform the design process, but it was not necessarily exactly how the paper then afterwards reacted, because there was a lot of things that we had to calibrate in the sims and how the sims were done, and the sims were being done by different people, and so all of the human error sort of accumulated in our sculpture. So you know, it's something that we did that is relatively novel, and it's a default, by default is something that you always have to try to basically ensure that once you install it, it's all going to work, but it's never really going to happen. There are always going to be things that you never accounted for, even if you are to do millions of simulations in various different softwares and millions of prototypes as well. So these are some of the images of the prototypes that we did at the first few months with like the different origami patterns as well. We tested various of them and tested how rigid they could really be. And this is a picture of my colleague Andrew at like 3 a.m. in the morning, where he actually came up with the prototype and he tested it by putting it on his head. So you can imagine that at that time of the night, he was quite happy actually that it was started to work. But it took us a long time to get to something like that. And then you might see that the actual scale of this prototype is fairly smaller to what we actually had. So our folds as well, because we had to cover such a large distance, we had to make them bigger. And they did not necessarily behave in the same way that these ones were behaving. So, you know, I'm not gonna lie to you. In reality, the way this was then performing in the space was relatively, or not necessarily how we had intended it to be. But it was still a fairly adventurous project, and we were pretty happy with how it looked at the end, how we were able to make a statement of, look, we've been able to build something this size just with used paper that you had otherwise just discarded and basically never saw it again. The colors are just the lights. There are no colors in it. We didn't paint it or anything like that.
And this is just bond paper.
Yeah, well, it was sewn with thread, and we had to have like mechanical sewing machines that were actually used for quilts. Yeah, yeah, to do this. So there was a lot of hand labor as well. Like you know, some of the pictures that I've shown in the office, that's how the Toronto office was like all full of paper. And of course, as I said, this director that we had in Toronto was very supportive of the project, and he was very happy. But we needed a lot of support from pretty much everyone in the Toronto office to come and help in, you know, weekends and stuff like that. But everyone was very like you know, proud of doing this. So yeah, I guess we were very lucky. Now, this project that I'm going to show you has a completely different scale. I'm not sure if you're familiar with it, but it's the Metropole Parasol in Sevilla, in Spain, by architect Yuri Meyer, and it was done by Arup out of our Madrid office. It's quite an intervention in such a historical part of Sevilla, and it had a lot of different reactions from the neighbors, and from pretty much everyone in Sevilla had something to say about this, and I think pretty much everyone in Spain too. So it took a while for people to really see the benefit of this structure in such a historical place. Now, I'm going to talk to you a little bit about the actual like scripting, parametric design of something like this, because of course you could also do it without any of this optimization, but it won't look the same and it will be a complete waste of money. So what we did was we've basically had a thickness and a joint type as the two parameters that we were able to change. We not necessarily went into changing the geometry. That was something that the architect discussed with us and we worked through as well. But we decided that the actual rectangular grid was a good grid, and we kept it. So the only two things that we were actually manipulating when we came to structural analysis were the the thickness and the joint type. What happens is that we tested how good were those two, were basically each of the planks performing. If they were within capacity, then we will actually say, okay, it's okay. We will obviously start at the thinnest thickness and at the lower number of bolts per joint. If it wasn't enough, then we will go up on the loop and upgrade the loads, and then upgrade the joint and the thickness and come back to the check. All pretty boring stuff, right? So I'm not going to spend more time on it, but it was quite an interesting project because unless you might be thinking there were no drawings done for the fabricator. There were drawings done for the planning authorities because they needed to see how this structure was going to look, because bureaucrats like paper, but fabricators don't really like that and don't really find it useful. They found fairly useful to have this spreadsheet with every single plank, thickness, and geometry, and knowing how many bolts had to go through each of these planks, and basically having the geometrical pattern of these planks to be able to cut them. And for the workers on site, it's exactly the same thing, because something like this is pretty much a Lego. And as soon as you know what part goes with what, it's fairly easy to put it on, like to erect it. This is the robot that was used for the fabrication. So this robot was actually running for 367 days non-stop to cut all of the planks that were used for this project, and it was done out of a company in Germany. I can't remember the name of the fabricator in Germany, so you have to excuse me for that. But this is how the planks arrived to site.
What is the plank material?
Oh, sorry. Yeah. So the plank material is CLT. Yeah.
It's what?
CLT, cross-laminated timber.
Oh, cross-laminated.
Yeah. These are all of the steel joints as they arrive to site. And this is how they started putting together this structure. So you can really see here, I guess you can see it there too. You can really see here what is the scale of such a structure. I mean, that's a person right there, and this is just one of the piers of the parasol. Now, because this is a sculpture that is done in a plaza, you have free access and you can really build any temporary supports that you want to build something like this. If you were to build this as a bridge, then it would be a completely different story, because you'll have much more restrictions as to the traffic that you need to allow to make sure that passes underneath. So they install all of this scaffolding, okay? And you might think, oh wow, but that's such a waste of money and resources. Well, yes and no. I mean, because working at height is something that you really want to avoid when you are a contractor and when you are an engineer. Well, I mean, when you are doing a project like this. What they did was building all of this scaffolding to actually build a raised platform. Once you have that platform, then there you can have toilets and you can have facilities for the workers. So the worker goes up once a day and it comes down once a day again. You don't have workers going up and down all the time. All of these are things that, if you are a good architect, good designer, you need to think about when you're designing your own works. Because in paper, everything looks very okay, but how you actually take it to practice is a completely different world. So, having built this platform, it was relatively easy to then have a crane and have all of these pieces delivered to this level, and then started to mounting them there. And they didn't have to go anywhere else, right? They could be installed at this level and then just connected to the piers. And then what you do is you take down all of the scaffolding. So this is how it looked at the end. And these are just some views of the structure from the top. There is a very nice video that I'm not going to have time to show here, but it's on our website in Arup. I believe it's in Spanish. It's never bad to practice Spanish, but it's also subtitled in English. And it really gives you an idea of the project, besides just the engineering side of it, but also how it is that they make this neighborhood felt revamped, remade in a way. Because it was fairly depressed after one of the markets in this area closed down. And now it's a completely new area in Sevilla. A lot of tourists come through. This has had a lot of vitality to the city. Now, I don't know if I'm doing well on time. Probably not. This is the last project that I'm going to show you today. And this is a pavilion that we did at McGill. It was part of one of the courses that I taught at McGill when I was adjunct professor there. I'm still collaborating with McGill, and there is a second pavilion that we're currently working on, which I haven't included in this presentation because it's a little bit premature. I mean, I'm hoping that we're going to be able to start fabrication in the next months, and then it would be something that I like to show to people, but until that happens, I prefer to keep it secret. So this was done by students. So it was designed and built by students. And I like what you might think. I was coming off from the AA, so I was fairly used to build things and have the school supporting that effort and the university supporting that as well. And I would say that it was clearly the case in Europe, and it's perhaps also the case in the United States. A lot of the schools are really going to build things in one-to-one scale, and there are not that many restrictions. But it was the first time that something like this, to this scale, was built in McGill. So there were a lot of questions about liabilities, and you can students really build things. I don't know, you tell me if students can really build things, but out of, at the end of the day, students are at school for a number of years, and when they get out, they're going to build things, right? So they better get to build them while they are at the school, and really know about fabrication and construction processes while you are at the school. Because later, if you don't know how things get built, then it's a real issue. Because in my experience as an engineer, when you don't know how things get built, then your building, your structure is never going to look like you once first thought it was going to look like. And I was talking to Tristan before. Contractors, there are good contractors and there are bad contractors. Good contractors will always try to push you for more efficient ways of doing things, and they won't just leave it all to bad quality as a way of saving money. But you have to watch out for both. So the more you know about how your building, how your structure is getting built, the better. So what's the concept here? It was to create structure that was actually playful with people, and we did that by combining continuous surface, a Mobius strip, with a moiré pattern. So the idea was that when people were to approach this sculpture or structure, we were kind of like playing with the way they were perceiving it through these two movements. Now, how do you actually resolve that into creating a sculpture, creating a structure that can actually be built? Is we had to create an irregular truss that was actually following the Mobius strip, and then we had steel bars to do that, but we also had ribs in plywood that were picking up those forces. Then the moiré pattern was actually applied to the sides of the truss throughout the whole Mobius strip, through the whole continuous surface. All of the elements were designed and were also modeled in Grasshopper and Rhino, because we couldn't really afford not knowing exactly what these angles were going to do and what these bars were going to do, because we will really then never achieve this geometry. So our tolerances were fairly low. I mean, the tolerances that we had were 2 millimeters for the steel bars. And so all of the irregular angles that we had were actually impossible to build by hand unless we could CNC bend them. And of course, all of the ribs, all of the plywood ribs and all of the ribs on the moiré sides were also CNC'd. So these are some of the first planks that were getting cut at the CNC machine at McGill. Now, in order to make sure we knew what was going connected with what, and because we didn't want to use construction drawings, because, you know, in my opinion, like in the other structure, construction drawings are something that, I mean, I'm not going to enter into whether they're going to disappear with time or not, but in reality, you should aim to design structures that do not need a huge package of IFC drawings, of construction drawings. For this structure, we didn't do any drawings, and students didn't need them. But that wasn't because they knew the structure well, because they had designed it. I mean, that happens all the time. It was because we were able to build within the whole coding, within the whole, within all of the elements, a naming system that tell us exactly what was connecting with what and where. So all of the bars had a coding system that was saying to us, this connects with element C20 to 120, and it also connects with element C05. This is a picture of the joints that I spoke about before, which were all CNC bent. And again, if it wasn't because of this technology, we couldn't have done this irregular truss with such a large number of different angles.
What was your angular tolerance?
The angular tolerance was about 1 degree.
1 degree.
Yeah. I mean, the structure in a way was still, because it was a lightweight structure, it was still able to take a little bit of movement. You know, all of these joints were pinned, so the bars were able to rotate and accommodate. But if we were to really start losing those tolerances pretty much everywhere, and then you would have ended up with something that would have looked completely different.
No eccentricity issues there, those nodes?
In here?
Yeah.
Eccentricity meaning because of the loads coming outside of the, yeah, there were things like that that I had to look at as for the structural design. But I mean, the loads of this were relatively low. We had a case where we had snow up to 1.2 meters or thereabouts, but it wasn't all on this part. It was on here, and we had a few inches of snow on top of this, and that's relatively normal in Montreal. But no, the structure didn't suffer at all. I mean, I think
deflection. Did you measure any deflection?
No, I mean it was like basically it just didn't react to it. So I think snow codes in Quebec are fairly conservative. So unless it's, you know, if you're talking about a roof of complex geometry or something like that, then perhaps they're not actually. But something like this that is relatively lightweight, there's not that much of surface accumulation for snow anyway. So, and this is a view from the inside with some happy students enjoying their work. And I'm just going to end the lecture with a short video on this pavilion, which I hope you enjoy. And you know, if you have any questions or anything, I'll be happy to take them, and you know, we can make this a a discussion or sort of a debate if there is anything that you want to discuss further. I'm okay on time? Yeah? Okay. Thank you. Thank you.
How did you bend the two pieces?
Sorry?
How did you bend the wooden pieces?
Oh, the Mobius.
Yeah.
Well, the ribs, and perhaps I can show it. Which one would it be? Yeah, okay. So these were not bent. These were planar. These were all cut out of a plane. The other pieces that were actually placed on either side of the truss, we had to look at how much bending they could take without doing a steam bending. Okay. So in reality, when you see them that they curve like that, they're cut out of a plane. But what happens is that we stagger a few of them. And that's how we actually get the planar curve to be, fairly curvy. But they are bent slightly on the other plane. They are just regulated in such a way that they don't go over a certain amount of angle. So I think if I remember correctly, it was something like 8 degrees, how much we could really bend them so that they could not come out of a plane. And to be honest, some of them in some areas actually came out because the connection in between the segments, in some cases was done by hand, and in some cases it wasn't that good, that well made. Some others were able to resist quite a lot of bending, but so.
At what point did you decide to submit to the paperwork, or were you invited, or did the proposal just caught your attention? Or?
Well, I collaborated with the guy that organizes the call for interest is an architect in Toronto, and he's really pro sustainability, and he runs this group. I collaborated with him the summer before, doing a few canopies for an art festival in Toronto. That was a small intervention because it was mainly cardboard tubes used to basically suspend some toile, like a sort of clothy roof membrane. So we did that work, and we always said that, okay, so next time we should do, like, you should present to this competition, and you guys should put something together. So he runs this call for interest or competition, whatever you want to call it, in a fairly open way. So if you really have a good idea of reusing materials, reusing paper, then it's a great venue to present your ideas to, but it's fairly flexible. So pretty much anyone can actually do it. It's not like they invited us because we were Arup. In fact, there were another architectural firm that also put together a pavilion, which was quite impressive. The rest were artists, in Toronto that were doing work out of their own hours and stuff. So
all these projects are really beautiful from like small scale to large scale, but I'm sort of wondering a lot about digital design. How do we take this from these like very specific custom jobs to something that can be more democratic as far as who has access and who could commission this kind of thing?
Mm-hmm. Yeah, and I think that's my continuous question, like my continuous fight, because as you are saying, I've chosen fairly nice looking projects, right? Because I'm not gonna come here to talk to you about concrete structures that you can see every day. But it doesn't mean that you can't use advanced computation to design something that you would call traditional. Or I'm just gonna give you an example. Like, we do use advanced computation, meaning scripting and linking the analysis model with the geometry and being able to change all of those relatively quickly for doing something as conventional as a concrete foundation. And there you're dealing with contractors that are not interested on a paper structure, they're interested on saving concrete and saving steel. But what you can do is you can use advanced technologies and computation to save you time. So instead of you becoming a robot, you let the computer become that robot, do all of those calcs and checks, and then you focus on the real things that an engineer should be focusing on, which are the actual overall design verification. So does this whole thing make sense? Is this a black box? No, it's not. I actually know why it's doing this and that. That's perhaps the extreme case of the use of advanced computation, but it's an example where we're not coming up with a product that is fancy, but we're using it to help us doing a task that otherwise will be really something we don't want to do.
Can I ask a question on that, or
Mm-hmm.
to sort of expand the conversation? So you used two words that I find interesting. You use democratic and access. Why do you find this word to either be non-democratic and non-accessible?
It has a lot to do with more the design of these projects and how we can push something forward on that. I mean, a lot of the critique of digital design and architecture is that it becomes this unwieldy, sort of expensive beast that sort of pushes back a lot of the parts of the project that it shouldn't. And I mean, with this project, it's beautiful. It's part of the campus. It has a lot of, the students have access to this, but you look and the donor list is giant. It's these sort of, how do we make this more of something that can happen, is what I was trying to ask. rather than be these very, very specific incidents for huge lists of private donors or some millionaire somewhere. How can your average person have more access to design? I mean,
But
yeah, basically.
yeah, but like, you know, all steel fabricators are using plasma cutters, and they could all run them through coding. And so basically, it's the same cost in cutting, as far as it's the same length, it's the same cost in cutting straight line that when you cut a curved line. So, you know, I think the fabrication tools are there, they're just not fairly well used. And I always put this example of like, you know, we've been building cars for how many decades, and the cars have complex shapes. They have doubly curved surfaces, and they're still being built, and they're being built by people that, you know, are not perhaps like high-skilled workers. But for some reason, the construction industry is always at the back of the aeronautical and automotive industries. And even though they could really take advantage of the technologies that are already there for those two other disciplines, they tend not to do it. And I always wonder, why is this? Because I was on site with one of a fairly large bridge that was being done in steel. 2.1 kilometer bridge with a box that it's like 5 meters wide at the top, 3.5 meters tall. We had a lot of non-conformances because the stiffeners were all misplaced. It was a real mess in terms of like where the welds were being done. They had switched some of the stiffeners, thicknesses. And while I was doing that, I was building this. And I was there with the guys on site and with the fabricators, and I was like, well, guys, why are you not just including where the stiffeners are when you cut the plates? It's as simple as that. They were measuring with a tape. I was, you know, coming from Europe and everything, I was like, this cannot be happening. They had the technology. I feel sometimes the construction industry is afraid of really making use of all of the powerful tools they have. And when I started, I said that there are good contractors and bad contractors. And I actually was pretty lucky of the actual chief of the construction company for that bridge was a pretty smart individual, and he was all into, you know, new technologies. And we used to have conversations about 3D printing. I have a 3D printer at home, and I used to bring him like models of the, you know, of the bridge and how we could like make it and stuff. So he was very open to that sort of thing, and he's the type of person that would be really interested to know from you if you have a good idea to accelerate fabrication and accelerate construction. So even in something that has been done for years, you can always find how to make it better, how to make it more efficient. And digital fabrication tools are there to make that happen too. But I honestly think that, you know, it's a combination of a lot of factors. Perhaps a little bit is, you know, architects should really empower themselves in knowing how digital fabrication tools really work, so that you can be in a meeting and you can push the contractor and you can push the fabricator and say, guys, we can do this because I've done it before. All we need is this, this, and this. And then the other guys are never gonna say yes if you're saying, they're never gonna say no if you're saying yes to a few $1,000s being saved in time and materials. So I agree with you, I don't like this idea of parametric design always right next to fairly fancy projects, because day to day you don't necessarily work all the time on those projects, and that's maybe not even the right way. Parametric design and advanced computation should really be the move for pretty much all projects.
Can I follow up on that?
Yeah.
Your thoughts? At a very high level, it was very articulate and granular answer. At a very high level, I would argue that the problem is we typically start with a formal idea, and we try to force a constructive system onto a formal idea. And those two things don't necessarily work. So you have to like really be willful, and you have to like just put a lot of force into it, right? You have to ask for volunteers, and you have to get the list done. I would argue that parametric design is rule-based design, right? right? So you set up a series of rules or set up a series of parameters or a kind of design space. In my mind, working with a material logic and a construction logic and the system of aggregation, if you will, or however you want to think about it, but you start the opposite way, right? You start from the brick, not from the arch. And you ask the question, what are the limits of the brick? And this is this sort of quant thing. You ask, what are the possibilities of the brick? How far can you push the brick and the brick relative to the brick and the brick relative to the brick relative to the brick, et cetera, et cetera. And then, a formal solution can grow out of a constructive constraint. Does that make sense? And I think we start way too often with this sort of formal idea, and I'm guilty of it myself all the time, and we try to then force a solution onto the formal idea. If you reverse that and you start from a system-based approach of design, which has kind of flexibility, if you will, and you say, okay, what does the brick want to be? I mean, Lucan really had it with that.
Yeah, and I think, a lot of times you will hear that an engineer says, well, yeah, we had a meeting with the architect and they had this idea on sketch and paper, and now we have to make it work. And I really hate that because, that means that you guys come up with a nice formal idea and then we come into play and we sort of like kill it because we started to standardize it and we started to, perhaps like, not killing, but removing a little bit of the real design aspects. And it's true that I think as designers we tend to think on how the final product is gonna look like, but we always have to come back to what is my unit, how am I building this, what's my material. And it's only when you actually go to understand that relationship that you can make up the actual final product. So it's a little bit of bottom-up approach more than the top-down approach. But it's fairly difficult, to do it. I mean, to really get into that more.
So I could ask 1,000 questions because this is like a good version of the thing. This is what I aspire to, so I was very pleased to see the work. Which question do I want to ask? I want to ask the question on the paper project, the origami part. Mm-hmm. So, and it's really a philosophical question because you're trained as an engineer. Mm-hmm. You clearly have a high level of artistic and design aptitude that you apply, right? It's how you approach design. But there must have been, I'm assuming, there must have been something in your engineering brain that said, this has some problems, right? Mm-hmm. In terms of an idea, because of the scalability of paper, the scalability of the fold and the hinge and all that kind of stuff. But you turned that off somehow and you allowed yourself to go into this kind of suspension of disbelief, let's explore. So I'm curious, just because you're like this weird hybrid, and I think it's great, how do you deal with that, almost like emotionally in terms of how you enter a project, when you know that there's some basic principles that you might have to turn off? And the reason I ask that, I want people to understand why I'm asking that question, because I think we need to develop a methodology for experimenting and failing and learning from our failures, right? What I think is so beautiful about the project is that you allowed yourself to go down that path, and it didn't have to form, and you learned a lot, right? You were willing to go down that path, and I think that's the kind of mentality that we need to inspire our students, right?
Yeah, I mean, it's actually quite difficult for an engineer to switch off those. And I'll tell you my story. I wasn't born as an engineer. In fact, I think when I was little, I always said to my parents that I wanted to be an architect, a pilot, and the world champion of gymnastics, because I was in gymnastics at that time. So I don't know where the shift happened to engineering. I think it's because I was good at maths and at physics, and I had a very good teacher that was very keen for me to go into engineering, and he was always recommending that I would do that. And he always said, if you ever want to go back to architecture, you can always do it. I said, okay, yeah, life is, at that time, life looked very long, and I had a lot of time. So I said, fine, I'll go into engineering. But the first years of engineering, I actually did a lot of drawing and a lot of painting as well, because I used to do that anyway in the summers. So I was still a little bit of a hybrid. And then as the courses passed by, I was more into maths, physics, and in a way, I think they shape our brains by taking out possible solutions in such a way that I think architects start with a problem, looking at every possible solution. We engineers, I think that process of like thinking of all of possible solutions, it's like 5 minutes until you start discounting options, and you get into, I know this is more efficient than this because I read it in this book, and because I did this calculation, and so yeah, so I'm going through this path, and it's a path. And your brains think more like a tree, like a branch. And I realized about this because one of my best friends from the Architectural Association, we were working around London, and he was poking me with questions like, okay, so let's think about that building, and how would you have designed that building? And I automatically started thinking about the constraints. That's how I would start to resolve my problem, by pulling out all of the list of constraints. Therefore, I can't do that, so I'll do this. It's like, no, design, don't think, just design. And I realized that that's sometimes the problem, that engineers do think about all of the constraints. So in this paper structure, there were some times where, I was really like getting worried that, oh my God, this thing it's not going to make it, it's going to fall down into people, and then what's gonna happen? And it's funny because I was sitting in Montreal, I had those moments, but then we basically changed the structure in such a way that I was satisfied with how much load it could actually take, etc. But there was this other guy, Nick, who was sitting in the Toronto office, and he was sitting literally one desk away from the director that supported us with this project. And that director was every single morning passing by his desk and saying, putting his arm on the shoulder and saying, "So Nick, this thing is going to be able to carry all of the load. It's not gonna fall onto people, right?" Nick is an architect, and he was like, "Oh yeah, for sure, we're taking care of everything. Everything is under control." And he would call me and say like, "So Maria, so what are we doing with this? What happens if this happens?" And then, it's obviously something that it doesn't come in a code. I think engineers tend to just go to the code and take the code as if it's some sort of Bible where all of the responses to your design questions are written. And I don't think that's the way you can possibly design at least anything that is going to be novel. So in this case, there was no design guide. I mean, we had examples of the work that Shigeru Ban had done, and we could do prototypes, and we could do our own testing, but we couldn't really say, oh yes, article, 5.1 says that we need to consider this, and that's what we are doing. Therefore, as if we were lawyers, we're clear and we discharge our liability, and that's it. But that was part of the plan, and that was part of the project itself. So I actually enjoyed it a lot. They actually like having that thought of not knowing how it was going to work, then test it and realize and reassure you that actually we're going in the right direction. And as I said before, we had a limited amount of time, so we only got to where we got. I think if we were to do that project now, we would definitely do it differently. We would approach certainly the way we did the seams in a completely different manner. And we would probably change also the size of the origami and perhaps other things too. But
that's a great project. Any final comments or questions? Okay, well, thank you, Maria, again.
Thank you.